Okay, so let's talk about this, how we could advance this high chem approach. The high chem approach required some experiments, and I would say reactive experiments, meaning you have to conduct a reactive experiment on the fuel to train the parameters of the model, or to get the parameters of the model. And we're trying to figure out now a way, can we replace the need for these reactive experiments and actually account for the real fuel variability and make a predictive model. So the approach came back to, again, the hypothesis that the functional groups do relate to the combustion kinetic properties. And we call this FGMech, which is the functional group mechanism. The philosophy of this approach is that the mechanism or the kinetic model can be entirely built from the functional groups. So how can we do that? And we need to, again, do the same thing. We need to get thermodynamic data, because even in a high chem approach, species have to have thermodynamic data, the fuel, the intermediates. You need to get transport data like we talked about. And then we need to get kinetic data, which are the rate constants for the different reactions. Again, the reactions here are a lumped reaction step, fuel going to intermediates. And there were a number of reactions involved. There was one reaction for the pyrolysis, and then 6 other reactions for the fuel reacting with a radical. So it's a total of 7 reactions that you need kinetic parameters for. And again, so you need kinetic parameters, thermal parameters, and these stoichiometric parameters. And we need to figure out a way to get all of these only from the functional groups present inside of a real fuel. So, of course, we need to know what is a fuel, right? Because the fuel functional groups are necessary to build this model. This can, again, be done by NMR or by a detailed hydrocarbon analysis that's typically found in a ASTM standard methodology. From that, from a characterization of the fuel, and of course, a non-reactive experiment, simply the fuel. You're not doing any special reactive experiments. You're just measuring the functional group distribution of the fuel. We can get the different functional groups as we did before. And first thing we can do, we can get thermal data. Thermal data is done from these different functional groups. We can estimate using something called Joback method. It's a group contribution method. You can estimate the critical temperature, critical pressure, and boiling point. And if you remember the transport lecture, we could get all of your transport properties like the sigma Lennard-Jones collision diameter, the epsilon Lennard-Jones collision weld depth from these 3 properties, and the molecular weight, so a reduced mass. So we can get these things, and we can get the transport data. We could fit this into the model. Another thing we need thermodynamic data. Well, again, go back to the thing I told you which was pretty bad, Benson's group additivity, but we're going to use it nevertheless for the first approximation. Benson's group additivity said if you knew the different groups that are present in an individual molecule, you can get the thermal data for that molecule. We simply extend the same thing. If you know all the individual groups in a complex mixture, you sum them all together, you get the thermal data, the heat of formation, the entropy of formation, and the heat capacity. And of course, that's shown here. Of course, we do make a big approximation. We don't really know all the different optical isomers that are there in a complex mixture, so we can neglect. We only include optical isomers for some of the very important functional groups, and things like symmetry number will be neglected. So we will make a simplification to the entropy, and we will see then how that influences the model development and performance. And then the third thing you need are the stoichiometric parameters, the alpha, the beta, the gamma, delta 3, delta 4, chi. These are all the things that are describing the reaction equation, the stoichiometric parameters. For that, we trained a multiple linear regression model. So based on different functional groups, and I'll show you from experimental data available in the literature for individual components, we trained how the functional groups represent the stoichiometric parameters. And then also you need rate rules or rates, kinetic rate constants, and I'll talk you how we get the kinetic rate constants as well for functional groups. And all of this is put onto a base model, which is a standard hydrogen, oxygen, and C0, C1 model. Okay, so first, the stoichiometric parameters. Again, we need to predict in the HiChem model, the stoichiometric parameters are related to the yield of those intermediate species, which are very important. The ethylene, C2H4, the propene, the butene, isomers, isobutene, N-butene, the H radical, and the methyl radical. This is all part of the first reaction equation, or the lumped reaction equation. In order to build this, Professor Haiwang and his colleagues do an experiment. We say we don't want to do an experiment. We want to be able to predict these values from knowing the functional groups. But in order to do that, first we need to develop some kind of a training set. A training set to see how the functional groups present in a mixture actually influence the yield of different species. So we build a training set using models. So we took detailed models for N-alkanes, isoalkanes, cycloalkanes, aromatics. We built these models for 50 different fuels. And then from the model, you can start to calculate at different temperatures, what is the yield. For example, from hexane, C6H14 react with the H radical, the stoichiometric coefficient for propene, for butene, for ethylene, for H radical, for methyl. And like this, we get a big database for different pure components. What are the yields of these products? And then based on the functional groups present in those pure components, we train from these functional groups. This will be the types of the stoichiometric parameters that come out. Similarly, methane, benzene, toluene, these are harder, okay? Ethylene, propene, butene, H, and methyl, they come from the direct decomposition of the fuel. The fuel breaks down, it makes these intermediates. But things like methane, it happens from recombination. Methyl radical plus H gives you methane. Benzene, it doesn't come from the direct decomposition of fuel. Fuel doesn't break down to make benzene. Fuel breaks down to make acetylene. Acetylene then grows to make benzene. Similarly, toluene, aromatics. These things are not direct decomposition products of the fuel. So we couldn't use a model to predict the concentration of these things because they happen sufficiently later after the first pyrolysis of the fuel. So for that, we just went to the literature and we collected data for 123 different species, pure components. So we got from the combustion literature C4 to C16 data, 1 to 50 bar, 1,000 to 1,600 Kelvin, 33 data sets for alkanes, 23 data sets for isoalkanes, 38 data sets for cycloalkanes, and aromatics. And again, from all this literature data, depending on the fuel, they had measured things like methane, benzene, and toluene. We trained. We trained for, again, these 123 data sets, all the different hydrocarbons are there, the functional groups that are there. We fit a multilinear regression model to say what the yield of these components would be for the HiChem model. And okay, the fits are never perfect. Okay, these are not. It's not like you get one perfect answer. You see here when we make these correlations with the multiple linear regression model, there's scatter. R squared is around 0.92, so this is a predicted stoichiometric parameter against the actual value, which is there from either measurement or the detailed kinetic model. And we see here these parameters for ethylene, for propene, for benzene. They're a bit off, okay? R squared is around 0.9, but we're going to use it anyways, okay? Because it's an approximation to make a simplified approach for kinetic model development. And this is done not with any mixtures, right? This is done only with pure fuels. So alkanes, isoalkanes, aromatics as pure components. And we're saying that we build the model based on information we know for pure components, but we're going to apply this to real fuel mixtures which have the same functional groups. Then you can go, I won't talk into great detail. For the kinetic parameters, again, what we do is we use a kinetic model, detailed kinetic models for those 50 different fuels. And based on the rates of formations of these different species, we just simply train for the functional groups what would be the K for one individual reaction. Hydrogen abstraction by H radical, hydrogen abstraction by methyl radical, by OH, and so on. And then we sum up all those rates together to give us the lumped kinetic rate constant. Again, it's an approximation, but it's something we show it works fairly well. And how do we know it works fairly well? Well, we simply go and we compare the approach that we have with the HiChem approach. So we basically take the exact same fuels that the HiChem model was built on. So in this case, for example, Jet A1, Jet A2, Jet A3, Professor Haiwang built the HiChem model based on experiments for all these fuels. And then we use our simple correlation methodology and compare. This slide is showing the stoichiometric parameters. How do they compare between HiChem and our correlation? So for like lambda 3, lambda 4, the alpha, the beta, the gamma, the chi. Okay, there's some uncertainties. For this Jet A1, we get alpha is off, by maybe a factor of maybe 40% off. There might be 20% difference in the gamma. Similarly, for Jet A2 and Jet A3, we can get within, say, 20 to 40% of the actual values that he got from measurements. And generally, we think within a factor of 2 is reasonable because we'll show even with these errors, you can predict things like the ignition time fairly well. So then you go and start to validate your model. So here we did it against different gasoline fuels. How we validate is we just take the model that we've built using the correlation tools based on functional groups, and we compare it against experiments. And here we actually compare FGMech with one base mechanism, C0 to C4, with based on Aramco mech, and another one based on USC mech. And you see that the model actually does fairly well. And the differences in the model performance are only based on the difference in the base chemistry. And again, this is something that Professor Haiwang showed. Professor Haiwang showed that really the important thing you need to get right is the base chemistry to get global combustion phenomena correct. And in this case, we show if we use Aramco mech as the base chemistry, we get a better prediction of the experimental data for 2 different gasoline fuels. And we can also do speciation comparisons. So this is a measurement of, this is a jet fuel, POSF 5433, and this is the flame speeds for those fuels. And again, the model can work fairly well, okay, in predicting even species like ethylene, methane, and laminar burning velocities. And okay, you can read the papers. The papers are there. We've tested this for like 35 different fuels. Again, it works fairly well. Is it perfect? It's not perfect. I mean, it's an engineering approximation, but it's much easier than developing detailed kinetic models with all their uncertainties than around the surrogates and so on. And this is, again, to show you how the field adapts itself depending on the complexity of the problem. Sometimes you have various levels of complexity in your kinetic modeling approach. And the last set of slides are just, we've taken this, we've even done it for fuels that you could never even imagine building a kinetic model for. Like I started in the early parts of this week telling you about heavy fuel oils and vacuum residuals that are used in marine engines. These things have thousands of components. You would never build a kinetic model using surrogates. But we can use the functional group approach to predict even the kinetics of these things. So again, we have a vacuum residual. In this case, it's going into a gasifier and is burning inside of a flame of a gasifier. And you get major products like CO, hydrogen, carbon dioxide, water, methane. Some of these are governed by thermodynamic equilibrium. Some are governed by kinetics, like methane, and methane is the main one that's governed by kinetics. So we've done this thing for VRO. We've compared it against experiments that were done in a gasifier. I'll go quickly over these slides. And we build a model, and one of our colleagues here is doing these kinds of reactor network modeling. So a gasifier is not one model. So we represent the gasifier as a reactor network. So we say the feed comes in, and we preheat the feed, and we model the first zone of this gasifier as a continuous stir tank reactor, a perfectly stirred reactor or a jet stirred reactor. And then as the fuel breaks down to some intermediates in this CSTR, or perfectly stirred reactor, and then it goes into a plug flow reactor where more reactions happen. So this is what we call reactor network model. Sometimes we take complex systems like gasifiers, engines, turbines, and we represent them as two simpler reactors put together. And therefore, we can put the kinetics into these different reactors, like a perfectly stirred reactor and a plug flow reactor, and we can see, can we predict the global phenomena that we're observing inside the gasifier. And we built the FG mech for a heavy residual. Again, all you need to do is get all these gamma, delta, alpha, beta parameters, and then the rate constants. And we can do all of this because we just do an NMR analysis of VRO. And from the NMR analysis of the vacuum residual oil, we get all the functional groups. And then we predict all the parameters that are needed for the model. Again, this is stuff. You can read the papers if you're interested. I'll just show you quickly. We can predict things very well, like even the overall solids that are produced, like carbon, the liquid phase products that are produced, and even the gas phase products. And then the last chart just shows us, if you look at the different types of vacuum residual oils that are produced, in this case, 3 different types of vacuum residual oils, which are blended together with jet fuel, we can predict like things like ethylene, methane, propane, butane, and so on. And then we take this and we put this into actual gasifier model, and we predict the methane concentration. Even we can predict sulfur concentrations, hydrogen sulfide, carbon monoxide, carbon dioxide, and so on. And okay, I don't want to go into the great details of all these things about real fuels and heavy fuel oil and gasifier, because I think it's quite a bit beyond combustion. But I want to take the last, we have about 25 minutes left, and I want to kind of summarize what I tried to articulate to you guys, okay, in the last week, okay. And it was 5 days. It was a lot of material. But I come back to the beginning, yeah, the first slide I showed you. And let's say we are 5 days older than we were on Monday. But we covered roughly the field of chemical kinetics as it's evolved in the last 100 years. Yeah, in the 1920s, Hinshelwood, who won the Nobel Prize, again, this quote from his Nobel Prize lecture said, "Nobody, I suppose, could devote many years to the study of chemical kinetics without being deeply conscious of the fascination of time and change." And that's what we've talked about, time and change, how different processes are changing at different times, at different temperatures. This is something that goes outside science into poetry. But science, subject to rigid necessity of always seeking closer approximations to the truth, itself contains many poetical elements. And there are many ways in which the mysteries of this chemical change might begin to impress themselves on a young chemist. So in the last, we've talked in 5 days from the last 100 years, from very simple experiments, how people discovered this field of kinetics. Then I took you into great detail, about detailed reaction mechanisms and kinetic rate parameters, and even the tools that people use, experimental and numerical, to get rates and formations of species and measuring these things in high accuracy today. And then even how we come back to simplicity again in the last 10 years, because we need to deal with things like very complex fuels, very complex reactors in industries, we come back to simpler approaches. And again, in chemical kinetics, there's no right answer. Okay, it's like a work of art. Okay, I will say it's a masterpiece. Your model can be detailed. Your model could be simple. Depends what you want to predict. Depends what are the questions that you're asking. And I hope you guys liked kind of the overview. I hope it encourages you to learn more in whatever area you're interested in and the problems that you're interested in. But again, the area is extremely rich. I'd say in these 5 days, we touched upon some of the important areas that have been evolving over the last 30 years. But I encourage you, if you're interested, there's a lot more to learn about, like quantum chemistry and quantum mechanics and statistical thermodynamics. There's a lot more to learn about laser diagnostics and measurements and different types of reactors, then the entire approach of building lumped models and real fuel models. Many places you can go. So I want to give you guys a chance now, last 20 minutes or so. You ask questions, okay? Have a discussion. What do you guys think? Do you have any questions, doubts? Yeah, let's get some hand mic. Where is it? I don't see any mics here. There's got to be some. Okay. Well, why don't we hand this one around? Okay, questions. You guys get it? I'll talk up here. Does this one work? This is probably on. No, this mic doesn't work. Okay, you don't get a mic. I repeat. That's a good idea. Huh? Yeah, that's a good idea. But this one doesn't work. Yeah. Okay. All right. Okay, who's first? I'll go back down.
Yeah.
You're gonna pass it
I
to the next
have to bring it to the next person. So my question would be, we touched a lot on liquid and gaseous combustion. Could you comment on how solid combustion and the kinetics of solid combustion would be different? Just short.
Yeah.
I guess it's a big topic, but.
Yeah, I mean, I think it's a good one. Okay, so solids combustion. Now, okay, what happens really in solid combustion? I'll draw something, then I'll come back to the mic. Okay. I would say we know from solids, the first step in okay, you have a reacting solid. Let's say it's biomass, right? So in biomass, you typically have three major fractions, right? You have the lignin, the cellulose, and the hemicellulose. This is a biomass particle. You have lignin, cellulose, hemicellulose. These are chemicals. They're very complicated polymers. Like our vacuum residual oil, they're nasty. They have a bunch of oxygen, carbon, hydrogen. They're super long. They're polymers, yeah? And of course, lignin is the most complex polymer, the biggest one. Cellulose is a sugar, or a heavy sugar. Hemicellulose, also a type of sugar. That's what plants are made of. What happens in the burning process? Well, of course, this biomass pellet has to be heated up, but the kinetic approach is to assume that most of the important reactions happen in the gas phase. So the first step is what we call devolatilization. Devolatilization of the solid material into the gas phase. The same thing with vacuum residual oil. We are trying to model the gas phase reactions that happen after the initial volatilization of a heavy liquid. And the same is true in the biomass. You're typically first looking at, I say, the devolatilization of the cellulose, hemicellulose into the gas phase, and then you have gas phase combustion reactions. But of course, important to understand that devolatilization rate and then you can build a kinetic model for the gas phase species. And again, Ranzi's group in Milano has built kinetic models for biomass combustion, and that's the approach that they take. Now, what is the challenge? Well, what if pyrolysis starts happening within the solid itself? Let's say the biomass becomes very hot, like 700 degrees C. Well, then you're going to start having reactions already in the solid. So it's not necessarily lignin, cellulose, hemicellulose that are evaporating or volatilizing and burning. It's actually the intermediate products of that pyrolysis. So this kind of solid phase pyrolysis, there's research in that area, like Professor Green at MIT is building some models for solid phase and liquid phase pyrolysis. It also happens in like diesel injectors. If you have a diesel fuel inside of an injector going into a chamber, this injector gets hot over time, and eventually you form things like gum, like solid depositions inside the injector. And that's all not a combustion process. It's a liquid phase pyrolysis process of things happening inside the injector, and these gums form. And again, people try to build models for that. It's much harder because in gas phase, we assume these things like elementary chemical reactions and microkinetics apply. Molecules collide, they react. In liquids and solids, we have something called solvation chemistry. Or basically, it's not a gas, and we have freely flowing molecules. All the molecules are inside of some liquid phase solution, so to speak. And depending on the density of that solution, the nature of that solution, the activity of the reactions are different. And so these kinetics are more complicated, let's say. Yeah, it's a whole several lectures on their own to deal with how solvation chemistry influences the kinetics. But again, there's groups that work on this. Good ones, I'd say. Again, Professor Green's group at MIT. Linda Broadbelt in Northwestern University. Her group is very good in building mechanisms for like pyrolysis of plastics, of biomass, and different things, and reaction mechanisms. Yeah, so I think it's doable. Yeah, it's just yeah, a bit more. It's of course a lot more complicated. We're developing models for some of the lighter hydrocarbons, like biomass is not only lignin, cellulose, hemicellulose. It has also many volatiles. We call these volatile hydrocarbons. For example, you go to the forest, and it smells really nice, right? Why does it smell really nice? Smells really nice because the pine trees and the different biomass, they're giving off volatile organic compounds. These volatiles, they call them terpenes or terpenoids. Eventually, the trees use these to make their structure. But again, what makes the forest smell so nice are these terpenes. Isoprene, all of you today are emitting isoprene. It's the #1 biogenically emitted hydrocarbon, isoprene. So you guys are emission sources of isoprene. All trees are emission sources of isoprene. I have a hypothesis that in forest fires, the forest fire spread is also due to the combustion of these volatiles. And we're trying to test that now. Nobody has looked at this much. So we build gas phase kinetic models for these very light molecules, because I have a hypothesis that when the forest heats up by this fire, the volatile rate, devolatilization of all these terpenes and isoprenes increases, and they form ignitable mixtures in the gas phase, and therefore, as this flame spread could not only be due to the surface, it could be propagating through the gas phase because you have fuel, these fuels mixed with oxidizer. But okay, this is a hypothesis. We're trying to work with some people in fire community to look at this. Okay, another question? Yeah. let's get the mic down here. Hey, you're supposed to help Dave. He's here. He wanted to volunteer, and you made him do it.
I looked right at you. You just raised your hand.
Okay, this is like less related to like a combustion question, but
Oh, yeah.
I was curious, like if your lab all of a sudden got like unlimited funding, so you could do like whatever you wanted, like what would you do? Like what would you want to do with it?
Oh, wow. Unlimited funding, okay. It might be a bad answer. I'll probably keep doing the same thing I'm doing, yeah, because I like this stuff. I mean, I'm kind of interested also in industrial systems, yeah, and lab research. We might spend. It's actually pretty cheap. You might spend 500,000, 1 million, 1.5 million. But if you want to build an industrial plant, that's going to make something like, I'm interested to build a facility for making synthetic fuel from CO2 and hydrogen, yeah? And I'm trying to work with some companies that need like $6 billion investment. So yeah, if I had unlimited money, yeah, that's what I would do. I would try to build like large-scale industrial facilities to make like renewable fuels from carbon and hydrogen. I would try to solve problems like direct air capture, yeah, if I had unlimited funding. But probably I would say I would if I had unlimited funding, I would not only spend it in the lab. Yeah, I would spend it on real systems, which I think we could build, which would have an impact on things like climate change and energy systems or efficiency, because I think the technologies exist. We're just not putting enough money in those places. So I think if I had unlimited money, I would work to try to scale things that we know work in labs, right? And just try to scale them up. And that's because I'm an engineer, yeah? I want to see things at scale implemented in the real world. And I think there's a lot of good research people do. It's just a matter of taking it out of the lab and into the real world. And that requires a lot of money, yeah? A lot of money. But again, I can appreciate the more fundamental scientists will build a synchrotron in their lab, and try to understand very fundamental dynamics and go for the Nobel Prize. Great, yeah, that's another approach. But again, I'm an engineer, so I would build something big and then try to make a lot of money off of it. Yeah?
Hold on.
Yeah, he's going to go first, then maybe you pass it to Dennis afterwards. Yeah.
That's why you pay me the big bucks.
Maybe related to what you said just now, on the road to transition and decarbonization, what's your vision on synthetic fuels?
Yeah, so I've been working in this area for like last 3 years. I was actually seconded from the university to a project in the north of Saudi Arabia, okay? It's called NEOM, and it's a project to build, our first project was build the largest green hydrogen production facility in the world. I have a lot of presentations about this, but I won't pull them up. Give you an overview. So we take 4 gigawatts of renewable energy, wind and solar. You use half of that to make hydrogen, so about 2 gigawatts to electrolyze water. And you make from that about 650 tons of hydrogen per day. And that hydrogen will then be converted to ammonia by Haber-Bosch process. It's a commercial process, and shipped globally. They're going to ship the ammonia to Japan and to Europe, where they'll use it for renewable. So it's a way hydrogen and ammonia become a vector of carrying renewable energy from Saudi Arabia, where you have a lot of it, to other places of the world, like Germany, Japan, where you have less of it, Korea. That project will be running by 2026. And so I think hydrogen as a synthetic fuel, I think that's the first e-fuel we consider. Hydrogen is a fuel that you can get from renewable. I think it'll be feasible. Yeah, I think the electrolyzer, we worked a lot on the electrolyzer technology. So electrolyzers to split water, to make hydrogen, are very expensive today. Yeah, so most of the cost of the facility, half of it comes from the renewable energy, half of it comes from the electrolyzers. And we know renewable costs are going down, like wind and solar. Every year the cost keeps going down. And then the electrolyzer costs are high today, but just like solar, the technology will come cheaper in like 10 years. So I do think in like 10 years, you will have many more of these large-scale hydrogen facilities from renewables. Now, making ammonia, it's a straightforward process, Haber-Bosch. So from renewable energy to hydrogen, you lose 30% of your energy. So it's about 70% efficiency. From hydrogen to ammonia, you'll lose another 20%. So I've already lost half my energy, yeah, that I made from renewables going to make ammonia. You ask yourself, do you care? Well, of course you care about efficiency, but does that stop you? No, because there's no alternative, yeah? We do many things today, like run engines, which are 40% efficient, yeah, to the 50% efficient. Now, synthetic fuels like carbon-based e-fuels, like methanol, and we're working on methanol to gasoline. You can make gasoline-range hydrocarbons. You can make jet fuel. A lot of companies are trying to, a lot of startups now are trying to make jet fuel, synthetic jet fuel or synthetic kerosene from CO2 and hydrogen. There you'll lose another 30%. So your round-trip efficiency is down to like total 30%. But again, people will do it. I think the bottleneck for synthetic fuel production is the CO2. Yeah? Where do you get your CO2 from? Because if you have to react hydrogen with CO2 to make a fuel, well, you need to get your CO2 from somewhere. And CO2 is not so easy to get. Again, you guys who's attending the lecture from Howard Herzog, you either capture it from a facility, that's expensive. You need large-scale capture plants, or you go direct air capture. I think direct air capture is a dream, yeah? And I don't think it's ever going to be cost-effective in the next 20 years. I mean, I've looked a lot at direct air capture technologies. Even in the lab, they have a long way to go. So I think the bottleneck for synthetic e-fuels to make them like cost-effective are going to be, like getting CO2 capture and systems for distributing CO2 to facilities where they'll make it cost-effective. So that's my view. I think we start with hydrogen, ammonia, and then maybe technologies for CO2 capture and conversion improve over time. Okay. Yeah. Oh, Dennis had.
I have two questions. One, what the current challenges that you see in the community? The challenges that you face and like you think we face. This is the first, and the second one, how do you see the future of hydrogen and electrofuels?
Yeah. So when you said community, do you mean combustion community or kinetics community?
Both.
Yeah. Okay, I think combustion community. I think in the last 15 years, 20 years, I attended my first symposium in Heidelberg in 2006, Germany, and sometimes the symposiums they get kind of boring. Yeah, I think the community has been a bit our meetings are a bit too conservative. I don't know if anyone's tried to publish in combustion symposium. It's a quite painstaking process, rigorous process, and most papers are rejected, like 60%. So the next symposium, I think now the leaders of the combustion committee, like Professor Law and others, they're listening to the young people. Like, this is not a good way to run our meetings, because I think many young people have been disappointed. Combustion committee is being very conservative, not being ambitious enough, yeah? Because we got to be ambitious because the problems being faced by society are so big, and we're always stuck in little problems like nonlinear versus linear fittings for the flame speed, yeah? Like, that's not the biggest issue, or this rate is different than that rate, and why are your rates different? Well, yeah, these are concerns, but that's not shouldn't be the main thing we're meeting together every 2 years. Yeah, so I think the next symposium, the plan is the format. I don't know if you guys have seen it. The format of how the papers will be received and the presentations are going to be very different than the past. So some changes coming, and the goal is to encourage more out-of-the-box innovation, ideas, ambitious approaches to solving the problems that we face. Yeah, and yeah, I mean, I think the community has to be more like collaborative because everybody's fighting against combustion these days, in the public. Yeah, you get all this, and therefore, you know, people probably need to team together more to get the message that, like I said in the lunch, combustion is a solution to many of the problems if people understand this. Yeah, I think like hydrogen, electrofuels, they're going to happen, but it's going to be a long time. I mean, I'm working in a fossil fuel country, yeah, country that sells fossil fuels. They're also trying to move away from fossil fuels to diversify the economy because they see it's an issue. But you know, I think the view is, you know, economic growth, standard of living improving globally. These things keep on going at a faster pace, and it becomes very hard to move away from a very reliable resource. Yeah. And it is unfortunate because they have issues with you know, the climate and the environment. Again, and it comes back to combustion people. I think we can help solve a lot of those problems. Yeah. I think, yeah, hydrogen, electrofuels, electrification, all good, all going to happen, but not at the pace that we need them. And the best way to reduce emissions is improve efficiency. Everybody knows that. And yeah, improve combustion systems. These are the best way. And I think society will realize after 6-7 years that even all those investments were good, but then we got to now probably reinvest back into combustion and improving it. That was the last one. Okay, here we go. Well, you know, like, I mean, the point is, like, you know, I studied combustion, but then I go and worked in a project making hydrogen from electrolysis. Because if you understand the principles of science, of engineering, don't worry, you don't only apply yourself in combustion, right? And that's the good part about studying combustion. I think Professor Pitch said this, the types of problems that you encounter, highly nonlinear, the types of expertise, kinetics, thermodynamics, diagnostics, experiments, you know, these skills are readily translatable to many other fields. You should be glad you're not a material scientist that only looks at like nanoparticle synthesis and then characterizes it using like a Raman spectroscopy. These guys have very few skills which are translatable to other industries. Okay. Yeah.
Hiya. So I was wondering about coupling complex kinetics with CFD models.
Yeah,
so we have to sort of drive our chemical reactor networks with like LES, but we can't do both in one tool because it's very computationally expensive and there's not really anything out there that does accurate emissions predictions, especially for aircraft.
Yeah,
so I was wondering, what you think the art of the possible with that is.
Yeah. So like this high-chem approach, Professor Haiwang has worked with the group at Korea, which is not in Korea. It's in France. Yeah. Her name again? Ron. What's the researcher's name? I forget her name. Huh? Say again? Several places. Yeah. And Surfax, very good gas turbine facility, combustion groups in France, and they build large-scale LES models. So they have used the high-chem approach for real fuel combustion. Because it comes down, they can do the whole model. Like the fuel model is only 7 reactions, and however 10 species or something, right? And then your base model, they do a reduced mechanism, so they come to something like 50 species, 40 to 50 species, which is very small then for LES. So yeah, I think for real fuels, this is the future. We have to move away from like this kind of surrogate approach with hundreds of species, because anybody who does CFD wants less than 50 species. Yeah, LES less than 50, RANS less than 100. Yeah, DNS they want like 20 species or 15. Yeah, so I mean I work a lot with CFD modelers. You got to provide them kinetics which they want, yeah, which are compact. You lose a lot of the fundamental aspects, you lose a lot of the theory, but again, it's a matter of what they want to predict. I come at it from both ways, right? I think fluid mechanics is important, chemistry is important. A DNS simulation is very detailed in the fluid mechanics aspects, very crude in the kinetics aspects, and somewhere you come in the middle, right? I think reactor networks with detailed chemistry, like I show, like third reactor with flow reactor, they can help you in many cases, yeah?
Yeah, so I drive like my CRN by the flow field, but we're trying to link aerodynamic effects to what we're seeing with the emissions profiles.
Okay.
So yeah,
So
we
you
kind of
still
want
need
one
the
tool,
LES,
not three.
You still need the LES for the, yeah, for the aerodynamic effects. Right, yeah. So yeah, you can try things like this high chem approach. They even have models for jet fuel. If that's what you're working on, you could try it out. All right, we've come to the end. This is where we depart ways. I enjoyed, really, I enjoyed 5 days with you all. It went pretty quickly. Hope to see you again, maybe in the next symposium, some other meetings. But anytime you have any questions, Combustion Kinetics, you know, send me an email. If there's anything maybe I articulated, I kind of like this subject. Yeah, I find it interesting and I'm passionate about it. And I hope you found it somewhat interesting. Hope you learned something. And yeah, let's be in touch. So thanks a lot. Yeah.